on this, you would put in your exam scores here, these 4 exam scores. So if you made an 80 on this one, then you put in what you think you'll make on these remaining 3. Or you can just, put, let's say, if I put 70, 70, and 70, what that gives me in the end. And then this is your project. It's out of 100 points. So this is the max you can have. This is the sort of what you project for you to make. Honestly, I'd love for everybody to make 100% on the project. If you meet the requirements, then you will make 100%. But you need to meet the requirements. Y'all know what that is, I think. I can help you even on the project. If you finish it, 3 to 5 days in advance, you can send it to me and I'll review it and, tell you what you need to do on it. Class participation, really this should be 50. If you miss a lot of class, hey Steven, if you miss a lot of class, you'll get a little bit lower than that. And then your top 5 quizzes, these are each out of 20 points. So you have 1, 2, 3, 4, 5 quizzes, each out of 20 points. That's it. Like I said, just put in the values that you already have. And right now you have 1 of these exams, and you have 3 reading quizzes. Your class participation, if you have above 50% on Moodle, then that means that you're on track to get the full 50 points. Right? The 50 doesn't refer to points, it refers to what percentage of questions you're getting right, or what percentage of the total available points do you have. And if you have 50%, that means that, well, you could have answered all the questions but answered them incorrectly. Does that help a little bit? Do you understand? Yeah? So just download the spreadsheet, put in your exam 1 score, put in your 3 reading quiz scores, and then you can put in the remaining 2, sort of project what you think you might make. And then you can also drop some of those reading quiz scores if you think they need to be dropped. Okay? You look excited to be here.
Can't hold it in.
Can't hold it in. It's just bubbling over.
Just try to surprise you, but you got it.
All right. I had said there's a reading quiz on Tuesday, but of course, what?
There won't be.
There won't be, right? Because it's fall break. Though some of you, if you have evening classes on Tuesday, you might be required to go to those classes. I'm not sure, because you remember we lost the evening classes to Tuesday because of that hurricane. I mean, it was a hurricane, but it didn't really cause any damage. Okay? So just be aware that if you have an evening class, your faculty might be asking you to come to class. But we will not have class, and we will not have a reading quiz on Tuesday, but let's go ahead and do one on Thursday. And that reading quiz will cover the physics portion of Chapter 3. We're going to start on that today. But remember, the reading quizzes are previews of the material, so it's not necessarily just material that we've seen. We'll probably see some of it. So that's it, page 69 through... No? Oh, through 92. 69. Oh boy. I'll be looking for the big ideas though. I'll try not to ask, small things. So look at the big laws, specific heat, latent heat, temperature, the scale of temperature, conservation of energy, the definition of work and energy, those sorts of things. 69 through 92, up to energy in the body. So like I said, each chapter is broken into the physics portion and then the applications in the body. So we'll do the physics portion in the beginning. All right. We have a little bit left in this chapter dealing with the heart, or with the body applications, fluid flow. We're going to skip this section. I was reading this question, I just don't like the way that I wrote it, and I think it's just going to sort of confuse you. So we're just going to skip that. But it is very important, this idea of the capillaries, so make sure that we don't skip this, that the fact that the blood slows down when it goes into the capillaries, which seems to contradict what the continuity equation says, that when the area goes down, the speed should go up. But in the capillaries, the speed will actually, the area goes up, not down, because you have a lot of capillaries. On the other side? What do you mean?
The back.
On the back. The next page?
Yeah.
This page, intravenous medication? Yeah, we're going to do that right now. Listen, you're not going to have a problem like this. Your book goes through a problem like this, but I think it is important to just illustrate how we use these things like the Poiseuille equation and the idea of pressure. Like, for example, when we're doing IV medication. I think actually nursing students have to go through these calculations, or nurses have to go through these calculations themselves. Any nursing? I know there aren't any nursing earlier. Any former nursing students?
Oh, the one.
That's what I thought, yeah. Did y'all have to do stuff like this for IVs, calculating IV flow rates?
I haven't gotten that far yet.
Oh, okay. All right. So,
But you do have to do it.
right, yeah. So, as we read through this question, we want to pick out the things that are given. I have a bag that has a volume of 500 cubic centimeters. So I'm just going to write down these known things. It empties through a 20 gauge needle, and that has a diameter of about 0.6 millimeters. So the diameter of my needle is 0.6 millimeters. And I want to know, and it has a length of 2 inches. And we want it to empty in 30 minutes. So the time interval that we want it to empty in is in 30 minutes. And I want to know how high must the bag be hung. And then I assume the viscosity of water is there. Remember, this is our eta. It's 0.001. The units of viscosity are Pascal seconds. And the density of water is 1,000. That's rho. Kilograms per cubic meter. And the pressure in the vein is 2,666 pascals. And the pressure is 2666 pascals. Now, before you freak out too much, you're not going to have a problem like this. But as I said, I just want to illustrate to you that you can use the Poiseuille equation to find out something as simple as how high you have to hang the bag. Because if you want to have the IV go at a faster rate, then you would put the bag up higher. So now with IVs, they have pumps, so they don't actually do this anymore. But you can open the drip, right? But if you put the bag up at a higher height, then it increases the pressure where it goes into the patient's arm. All right, so I want my flow rate, Q, to be delta V over delta T. And that's going to be 500 cubic centimeters. Cubic centimeter is a cc, right? I've heard cc's before. That's what the C and the C stand for, cubic centimeters. 500 cubic centimeters over 30 minutes. But I want it to be in cubic centimeters per second. So I'm going to convert this minutes to seconds. And that gives me 500 over 1800, which gives me 0.278 cubic centimeters per second. So that's the flow rate that I want to have, that I want to get that amount of bag. I want to empty out that entire bag in 30 minutes. That means that I need to have a flow rate of about 1/4 of a cubic centimeter per second. Now, my pressure differential, well, I know also, erase this, that my Q is equal to pi r to the 4th times delta P divided by 8 eta L. So this is just our Poiseuille equation. And notice I have all these things. I know what my viscosity of the fluid is. That's my 0.001. I know the length of the needle through which the stuff is going to go. And then I also know the diameter, or the radius, is half the diameter. So I want to find out what should be the pressure differential. So I can solve this equation because I know everything except for delta P. So I'm going to solve this equation for delta P, and I'll say that delta P is equal to 8 eta Q, or eta LQ, divided by pi r to the 4. again, not going to ask you to solve this equation on the exam, but you do need to understand that we can use this information in order to figure out what is the pressure differential. That is, what is the difference in pressure across that needle from the beginning of the needle to the end of the needle that will get us this flow rate that we need to get to empty the entire bag in 30 minutes. Okay? Now, when I do this, if I want to get delta P on this side all by itself, there are a couple different ways you can think about it. I like to think of it as I want to multiply this whole side by the inverse of this pi r to the fourth over 8 eta L. And when I do that, it cancels out this and cancels out that. And then I get the inverse of that, 8 eta L in the numerator, pi r to the fourth in the denominator. Don't get bogged down with the algebra, okay? What I want you to see here, what I'm about to show you, is that as you change these different quantities, it changes the pressure. And, like, for example, if I had, say, if I had a bigger viscosity, like if my viscosity went up, then what would need to be my pressure differential? How would my pressure differential need to be different? Bigger, smaller, the same? Bigger. That sort of makes sense, right? That if I have a more viscous fluid, it's harder to push it through, so I have to apply more pressure. So if my eta increases, then my pressure differential has to increase. What if my length of the needle, if I just have a longer needle, what happens to the pressure differential? If L increases, what happens to delta P? It goes up, right? If I have a longer needle, that means that I have to push on it harder to get through that length of the needle. Similarly, if I have a bigger flow rate, if I want a bigger flow rate, then I have to add more pressure to it. But if I have a smaller needle, or excuse me, a bigger needle, then my pressure differential doesn't need to be nearly as big. Like if the needle is just a big old thing, it's not that hard to push fluid through that. So those are the sorts of questions that you'll see on the exam. You're not going to see a calculation like this. I just want you to see this now, but you're not going to see it on the exam. Okay? You're clear with what I'm going to assess you on?
So like you want us to know the concept and not the math.
I want you to know the concept, but I'm not going to ask you to solve the equation. You'll have the equation, but then I'll ask you questions about how are these variables interrelated.
Okay, so the radius to the fourth has no effect on pi to the.
The pi is just the constant. It doesn't
The
affect.
constant pressure difference.
The pi right here.
No, the radius to the fourth has no effect on the pressure difference.
Yeah, so if you increase your radius, if you make your needle bigger in diameter, it's just bigger around, then the pressure that's required is much, much smaller. In fact, if I increase my radius by, say, a factor of 2, then that means that my pressure differential needs to be 1/16 what it was originally. But there are various reasons for using small needles, right? But you don't want like a big garden hose stuck up in your arm.
So for Q, it goes up.
If Q, everything in the numerator, like if Q, if you want a bigger flow rate, then you need a bigger pressure differential. You need a bigger difference between the pressure on one end of the needle and the other end of the needle. That's what this delta P is. The difference in pressure from one end to the other end of the needle.
One more question.
That's okay, go ahead.
Okay, so on the original equation, I remember from Tuesday, the radius, when the radius goes up, Q goes way up.
Right.
And when the pressure difference goes up, Q goes up. But what happens to N and L?
Okay, it's not N, it's eta.
I mean,
Right,
eta.
yeah, so here, if the viscosity goes up, I'll think about it intuitively. If I have fluid flowing through a pipe that's really thin, like water, and then I replace it with, say, maple syrup, is that maple syrup going to flow faster or slower? It's going to flow slower, right? So if I increase this in the denominator, that means this goes down. This is an inverse relationship. If this goes up, this goes down. And similarly here with the length. If I have fluid flowing through a pipe this long, it flows at a rate, keeping everything constant except I make this pipe go from here over to Culture Hall, then my flow rate is going to be decreased. It's harder to push fluids through a longer pipe. Alright?
Everything on the bottom is basically inverse, and everything on top goes up.
Right.
Except the radius goes up a whole lot.
The radius goes up a whole lot. Right? If I increase the radius by, say, a factor of 2, then this increases by a factor of 16. And remember, this assumes that our pipe remains filled. So if I have a pipe, we talked about this, if I have a pipe this big and it has water flowing through it, it's full from top to bottom with water, and then I make the radius twice as big, so it's like this big, and if the pipe remains full top to bottom, then I think it would stand to reason that, yeah, I want to put a lot more water through this bigger pipe. Okay? Those are good questions, and those are really the types of questions that you'll see on the test.
That's what I asked.
Yeah, look at the old tests. They will give you a good feel for what to expect. I want to see some excellent grades on this next test. And those old tests, the practice that y'all are doing every single day, the practice that you're doing every day, right, that you're doing every day? Every day? 100%. The practice that you're doing will help you on the next exam. Look at those old tests, look through the notes, and then read the chapter. And most of the stuff in the book is fair game. I've told you at various points there are a few things that I'm not doing out of the book. Like, for example, I said this, but let me emphasize it again. The valves. There are a couple pages on the valves of the heart. Not going to see valves. You don't need to know the names of the valves. It's an interesting read, but you don't really need to know much about the valve. You don't need to know anything about the valves of the heart. But otherwise, everything in the chapters, unless I've told you otherwise, I don't think I've told you anything else.
So we don't need to know where the pulmonary veins and pulmonary arteries are?
Yeah, you need to know the veins and the arteries and the order of blood flow. I mean, I think that was on your quiz, actually, wasn't it? Yeah. Yeah, so you do need to know the order of the blood flow and just the basics of how blood flows through the heart.
And where it's located, the different...
Yeah, the atrium, the ventricles, right, left. Okay, so what was I doing here? Oh, so if I calculate this pressure, I know all the numbers. If I calculate the pressure, it works out to be 4,400 pascals. That's the pressure required to give me this flow rate. And then if I want to know the height, well, P, if you recall, is equal to rho times G times H. You remember, this is on your equation sheet. This is the pressure at a certain height. Like if I have a column of fluid, the pressure at the bottom of that column of fluid. And so here I want to know what height will give me 4,400 pascals. And so height is equal to pressure over rho times G. That's 4,400 over 1,000. That's the density right here. And G is the acceleration due to gravity, 10 meters per second squared. And so that's equal to well, I have 0.72, that's not right though. That's equal to 0.44 meters. Alrighty? Again, you're not going to have to work the math of that, but I do want you to know the relationships and how the fuzzy equation works and the implications of it. What if you have a blood transfusion? So instead of using, say, something like, I don't know, a saline solution that you're putting into the patient, but instead you're trying to put blood into the person, what would you have to do to the height of the bag? Let's do this as a clicker. So would you have to increase the height decrease the height, or would it stay the same? A, B, or C? And remember which variable describes the viscosity. You'll need to know the meaning of each of those variables for the test. It's not that far away, by the way, the test. All right, let's do about 5 more seconds. What?
That code that you gave us in Protect. Because I have a different class, so I switched.
You switch frequencies?
Yeah, I didn't know.
Hold on. Put in your answer again. I had to restart.
So do you know what I'm saying? I'm going to turn it off.
Yeah, so you're in frequency 8.
You can Australia or what?
Oh, okay. You're on frequency 8. That's what you need.
Thank you.
It should be. It's probably the same. All right. I'm going to stop here in just a few seconds. Just guess if you're not sure. All right, good. A is correct. Remember, the viscosity, that is that variable eta. And notice how this affects us as we move through, that if I increase eta right here, then that means that my pressure increases. And if my pressure increases here, then that means that the height of my bag has to increase. Right? That it just requires more pressure to push that more viscous fluid through the needle, so you have to raise the height of the bag. Like, that would be a good question for the test. Say that I have an IV bag set up and I replace the fluid with a more viscous fluid, or I replace the needle with, say, a bigger needle or a smaller needle, or I replace the needle with a shorter needle or a longer needle, then what would you have to do to the height of the bag in order to keep the same pressure? How would y'all answer that question? Let's say that I have a bag, an IV bag, and I want to keep the flow rate constant. And let's say that, I don't know, I use a bigger needle. I go from a needle that's itty bitty to a needle that's bigger like that. What would I have to do to the height of the bag then? Would I have to increase the height of the bag, decrease the height of the bag, or would it stay the same?
So you went from a small to a
Yeah,
big?
I go from a small needle to a big needle. Then what happens to the height of the bag? I go from a small to a big needle. Yeah, just like the other needle. I go from a small needle, I make the needle bigger. What happens to the height of the bag to keep the same flow rate? All right, let's stop in just a few seconds. Let's stop at 40. That's right, B is right. So if I go from a small needle to a big needle, that means that what's increasing? My R, right, my radius is increasing. So let's look at our Poisson equation. That's Q is equal to pi R to the 4th delta P over 8 eta L. I'm not going to rewrite it like I did up here, but let's just look at this one in particular. Now, if R goes up, which is what I'm doing, your delta P will go down. To keep the same flow rate, I want to keep Q constant over here. If R goes up, then my pressure differential, the difference in pressure, is going to decrease. And then, if my pressure goes down, P is equal to rho GH. If pressure goes down, that means that the height of the bag should also go down. All right? What do you do if don't know, like if you're attacked by a group of clowns.
He said go for the juggler.
Oh, I've already given you that one? Shoot, I'm sorry. What's the worst thing about living on O Street? I told you this one? What do you think is the worst thing about living on O Street?
It smells like spaghetti. Spaghettios.
No, this is where y'all say, I don't know. You say,
Oh.
yeah. You have to walk a whole block to pee. That's a good middle school joke. All right. Yeah, you should write it down. Squeezing the bag increases the flow rate. This is an application of which of these? So, you've seen go into the room and no squeeze the bag. What is, that's an application of what? All right, let's stop at 36, 37. All right, I can see how you might think it was Boyle's law. Because Boyle's law says that PV is equal to a constant value. Right? That's why you thought it was Boyle's law. It's not Boyle's law, however, because this applies to what type of fluids? Gases. Right. In fact, if you have an incompressible fluid, like water or some other liquid, you can't change the volume of the fluid. Right? That's the definition of incompressible. That I can't change V without changing the amount of material that's in there. So with a given amount of fluid, I can't change the volume. So Boyle's law is only for gases. I think that your book, and I might have even mentioned it, that they sort of cast Boyle's law for a fluid, but that's not for a liquid, but that's not really correct, because this is really only for gases, because fluids are incompressible.
I think that's what I was thinking of. I remember something in the book where they talked about it.
Yeah, I forget exactly where it was, but then they do say, the author does say, oh, but these doesn't really apply because these are liquids, not gases.
The reason is like squeezing the bag, that's the pressure part, and flow rate is the volume.
No, I mean, I understand what you're saying, but no, that's the wrong reasoning. Because the volume refers to the volume of the fluid. Now, when you squeeze the bag, the volume does go down because you lose some fluid, right? That's probably what you were thinking, right? But really, it's Pascal's principle. Pascal's principle, remember, I have this piston. If I push on it with a certain pressure, then I feel a pressure throughout. So with an IV bag, you want to get an increased pressure at the location where the medicine is entering the patient. And so you squeeze on the bag, you give a higher pressure up here, and then that causes an increase in pressure at the needle. So it's Pascal's principle is the answer. A is the answer. I can understand why you would put Boyle's law though, but it is still incorrect. All right, let's look at coronary arteries. Again, just how the Poiseuille equation is applied here. A coronary artery is an artery that can be blocked with cholesterol. We've already talked about how the coronary artery, or excuse me, that when you block it, that the velocity of the blood speeds up, right? That if I have an object, if I have an artery and it's partially blocked like this with some material, that the velocity here is small, but the velocity here is big. It goes a lot faster when it goes through that. Now, changing the radius also affects the blood flow. It's pi r to the fourth is the Poiseuille equation times delta p divided by 8 eta L. So if the radius goes down, that means that the pressure goes up. I mentioned this earlier, but let me restate it, and we'll restate it again soon. That delta P is the systemic pressure. The pressure in the entire circulatory system, not the local pressure. Right. It's not the pressure at this location, because we'll actually find that the pressure here goes down, but the overall pressure in the system will go up. That's when you talk about your high blood pressure. This is what we're talking about, that our blood pressure will increase as those arteries get blocked more and more. All right, let's try these questions. A decrease in the radius of the artery will require what change in pressure to maintain the same flow rate? An increase or a decrease or stay the same? All right, let's stop in a few seconds. 33. Okay, good. A is right. Again, from the Poiseuille equation, well, we saw this right here, that if I decrease R, that my delta P will increase. Let's go ahead and do this other one here. A decrease of 10% of R causes a change in the pressure of what? Is the pressure going to change by a lot or a little? That's really the question you want to ask yourself. All right, let's stop at 33. 33. Okay, let's see. C is right here. Again, you want to ask yourself, is it a big change or a little change? And because we have this R to the fourth relationship right here, this R to the fourth, that a small change in R will cause a big change in P. And so I know it's not going to be the same or smaller, so it only leaves C. You don't even have to really worry about the number, about is it 1, 8, 10, or 30. But is it the big change or is it one of the smaller changes? That's a good practice for multiple choice exams, by the way, whether it's in this class or others, that you go through and you look for the answers that are not reasonable. All right?
Process of elimination.
Right. And often on exams you can do that. On a good exam, you should be able to get rid of answers that are not reasonable. Okay. We're at arterial collapse. So when I have an artery that gets full up of junk, like this one, the blood coming through, we've already talked about, has a small velocity here and a big velocity here. That's just from the continuity equation. A1V1 equals A2V2. If if A2 decreases, that means that V2 has to increase. The continuity equation, which comes about from the flow rate that Q1 has to equal Q2. There's a principle called the Bernoulli's principle, and your book doesn't talk about this, but you need to know it in order to understand the arterial collapse, and it's just kind of cool. The Bernoulli's principle and it sort of says a lot of stuff, but one of the results of the Bernoulli's principle is that if the velocity goes up, the pressure goes down. And you see that in aircraft wings, airplane wings. If you've ever been on an airplane, your wing looks something like this. This is sort of exaggerated, but it looks something like that. That's the cross section of the wing. And then you have air that comes on both sides of it. Now the air, as it goes around this wing, you get these, say, two air particles that come along right here. One has to travel a long path, and one has to travel a short path. So, because you don't want to create a vacuum around the wing, like nature in general just doesn't like a vacuum, if you have two air particles, they're going to go around, and then they'll meet over here at the same point. They'll come back together. That means that at this side, it's going to travel slower or faster? Faster. It's going to travel quite a bit faster. All right, so I have a high speed on the top and a low speed on the bottom. High speed on the top, low speed on the bottom. And because of Bernoulli's principle, I'm going to have a low pressure on the top and a high pressure on the bottom. And if I have a high pressure, low pressure, then I have a net force that's upward, and that's called lift. So that's Bernoulli's principle, and that's the impact of it. Again, not in your book, Bernoulli's principle, I'm pretty sure. Y'all remember Bernoulli's principle in there? No. But it's an important idea to think about when we're considering arterial collapse. Because in arterial collapse, what you get is you get a high velocity. And if I have a high velocity, what does that tell you about the pressure here at this point? It goes down. It goes down. I get a high velocity and a low pressure. Now remember, if I restrict that vessel, my systemic pressure goes up, but the local pressure is going to go down. So here, because I have a high velocity, I have a low pressure. The Bernoulli's principle is the pressure at that location. But in the Poiseuille equation, that's not what we're looking at. We're looking at the pressure difference. The difference in two different points where the pressure is. The difference from the aorta to the vena cava, all the way back, from the highest pressure to the lowest pressure. Remember, the aorta has the highest pressure. That's just after it leaves the heart, after it contracts. And then after it goes through the whole systemic circuit and comes back, it comes to the vena cava at the lowest pressure. Oh, this is a little ping pong ball and a little votive candle holder thing. If I blow on this, if I put a stream of high velocity air above the ping pong ball, what's going to happen to the pressure? Because if I have a high velocity, what happens to my pressure? If the velocity goes up, the pressure does what? It goes down. So if I put a high velocity stream of air across the top of this little cup, then it's going to create a low pressure. Now the pressure inside the cup will still be high, right? It's just over the top I'll have a low pressure. And so I should be able to create lift, just like on an airplane wing. By putting a high velocity over the top, then I should be able to lift up the ping pong ball. You want to see? Oh, you see it? Lift up. Ooh. Isn't that cool? You can do it with a soda can too. Especially if you have like those little soda cans, they work well. They're little like 8-ounce soda cans, and you put them like in a coffee mug, and you blow over the top of it. It'll lift the whole can up out of the coffee mug. It has to be empty, of course, and then deposit it next to it. You know where they make those sodas? There's like those little cans. There's little cans of Coke. Mini soda. Oh, that was free too. I mean, yeah. Look, you get this with a hairdryer too. This is my hairdryer. It's a long time to dry my hair every morning. You've seen this before? Yeah, it's kind of cool. So, a hot stream of air, like out of the hairdryer, it creates this low pressure. So you get a low pressure here in the middle, but then you get high pressure all around. And so it's like you create this little tube of low pressure. And you can... Really quick, high velocity right here. So a low pressure, tube of low pressure, called... What's that?
Doesn't it have a little bit of has a release pressure because it looks like
A little bit what?
a box thingy. I don't know what this is called. Hydraulic lift thingy.
A hydraulic lift. Can you explain what do you mean? Explain the question.
You're talking about the principle that goes with the hydraulic lift.
Yeah.
The
Are we not talking about this?
no, she's saying, is it like that? Does it have to do with
like
something?
that as well.
Pascal's from
Pascal's principle. No, because remember, Pascal's principle is only for liquids. It's only for incompressible things. And this is a compressible thing. So you have to be careful. Various principles. Pascal is only for liquids. Water, hydraulic fluids, oil. Caleb? Caleb.
So this, started like this got to realize, oh, I'm losing my voice, sorry about that. But when I was younger, I got this kit that claimed to be able to levitate balls and stuff with your brain. Basically, I think that the force of like something moving up here or something was causing air to come out, and because you're a kid, you know, you're thinking that it's levitating when it's not. It's just creating that pressure thing, you know? And I believed it for years, and I was amazed for years, and now I know.
But it's different. I mean, part of it is just that the air is pushing up.
Mm-hmm.
And so if you have like a hovercraft or something like that, that's not Bernoulli's principle really. It's just, you know, pushing down with the air. Like there's a certain force.
Yeah, I never noticed that.
Okay. I'm not sure about the whole brain thing.
That's with the hovercraft. Wouldn't this principle be working in reverse because you're creating a rate of flow underneath it, which would cause a lower pressure underneath?
Like those airbag things.
I guess so.
And then they have things like inside of a glass or something, and then they make it all go up.
I don't know if she's not.
I'm not sure.
It's sort of like what you just did, but in like a science lab or something.
Okay. But this is like a science lab. All right, let's look at the lungs. We talked about the lungs. We good on this? You okay? All right. The lungs bring oxygen to the blood from outside air.
How does Bernoulli's principle relate to the arterial collapse?
Oh, because Bernoulli's principle says that if the velocity goes up, the pressure goes down.
Okay.
In an artery that's blocked, because of the continuity equation, the velocity increases. When the velocity goes up, the pressure goes down. So I get low pressure right here. And if I get a low enough pressure, I get higher pressures outside. They collapse it down.
No.
Okay. Yeah, so the high pressure outside of the artery is important.
That's what neurologists mean when they say they have a high pressure system and a low pressure system.
That's what they mean. And it'll move from high to low. The high pressure will push the low pressure out of the way. I think in your book they talked about that a little bit. All right, so the lungs bring oxygen to the blood from the outside air. Remember, that's what our pulmonary circuit does. It takes that used blood to the lungs, and they get that reoxygenate the blood. Boyle's law describes how air comes into the lungs. The lungs expand, and that increases V, and it decreases P. Remember Boyle's law, PV is equal to a constant. So the lungs are not muscles. Instead, the muscles around the lungs will contract or relax to open the chest cavity. To open or close, to open the chest cavity. Will contract or relax to open or close the chest cavity. We talked about this before, right? Practice breathing. You make your chest cavity bigger, you make it really big, then that decreases the pressure inside of your lungs, and then that high pressure air rushes into your lungs. Same idea behind the straw. But the straw, you create a small pressure on one side, and the high pressure pushes the fluid up inside your straw. Okay? And the lungs work a very similar way. If V goes up, V goes down, that's inhaling. If you switch it, that's exhaling. If V goes down inside the lungs, P goes up. You get high pressure inside the lungs, and then that forces the air out. Now the iron lung, I'm not sure if y'all have ever seen the iron lung before. We have a video I'll show you. But it's a device that helps you when your diaphragm muscles are too weak to help you breathe. So if your muscles get really weak, like for example, if you have,
Polio.
polio, like you have polio, then those muscles just get very weak and you can't move that chest cavity enough to breathe. And the iron lung helps you. It's a device. It's about the size of a person, because it has a person inside of it. Here's their head. Here's their arms. And they lay inside of the iron lung. This is all closed off right here, so that your body is inside this big barrel, but your head is outside of the barrel. And what it does is it has this pressure actuator that will cause the pressure in here. The pressure versus time will go up and down, up and down. So it'll go up for you to, gosh, what is that? If the pressure is big inside of the iron lung, what's that going to do to you? Are you going to inhale or exhale? I know what you're thinking, yeah. You're actually going to exhale. Like if you have a high pressure in here, it'll force that air out of your lungs. And then if you get a low pressure in here, it'll force air into your lungs. Let me show you a video that describes this. Was he in an iron lung?
No, but it did stunt his growth and it messed up his back. He had back problems for the rest of his life.
Really?
Yeah.
What's that? Yeah, can you imagine?
That has to be pretty boring.
I'm sure it's boring, yeah. Alright, I want you to know the basics of the eye. We're actually going to come back to the eye in a later chapter with optics, and we'll talk about eyeglasses and the light that goes through the eye. It's really interesting. But right now, I just want to know about the eye and the fluids that are involved, because it's kind of an important thing. The eye, the intraocular pressure, ocular refers to the eye. Intra, means like in, so it's the pressure inside of the eye. Pressure inside of the eye. A high pressure, that is, if you have a high pressure of your intraocular pressure, that's called glaucoma. So if you know somebody that has glaucoma, usually an older person, it's because their pressure inside of their eye is too high. And the low pressure, if you have too low of a pressure inside of the eye here, you'll get collapse of the eyeball.
Ooh, that sounds awful. Does that happen?
I think it does happen actually, if you get a low pressure. It could occur like if you're losing fluid inside of your eye, then you can get a low pressure.
All of a sudden, yeah, I just.
I've never seen it happen, but
Could that happen in a vacuum?
in a vacuum, it's just going to explode because you have a high pressure. Just pop. Yeah. Okay. Like you take a bag of potato chips up in an airplane, right? That's a lower pressure. It gets big, puffs up. You ever done that? Take a bag of chips on the airplane?
No, but I will make sure to do so.
Yeah, you should try that. All right. There are several parts to the eye. The cornea. We'll see this again later. But the cornea is the outer surface.
What if you took an empty bottle of water on a plane?
Yeah.
Yeah, if you took it.
Crushed like it did.
No, it wouldn't explode, but it would sort of expand. Like when you go up high up in the air.
With the water, the first day class, like as we went lower.
Oh yeah, the video we watched. Yeah, it'd be like the reverse of that, from the bottom up to the top. So if you take that bottle on the plane, it'll just sort of bulge out a bit.
I'm trying to figure out a way to ask this question without sounding crazy. But I don't know. So what's something we could take on a plane that would explode? Please don't take this down.
The pressure, your cabin pressure is maintained. So while the pressure is a little bit lower than what we have at sea level. It's not that much lower. So
So-
nothing really.
So that's why, like, it's not any different when they give you, like, your bag of nuts and stuff like that?
Right. It's not that much different. But it's enough different to see it. I've seen it happen before.
What if we went all the way to space?
Well, you would have things pressurized in that case.
What
Like
if
you
we
would have
just
a-
like camp?
Yeah, the bag of chips would just poof, it would just poof open. Alright? Anyway, aqueous humor. The aqueous humor is replenished and drained. You have two fluids in the eye. You have the aqueous humor and the vitreous humor. The aqueous humor is right here. That's the fluid in that part of the eye. The vitreous humor is right here. The vitreous humor is used, well, let's see, the aqueous humor brings nutrients to the eye. And that's why it's replenished, it's drained. It also takes away sort of waste products. You can have issues with the aqueous humor if you don't, like if it doesn't drain properly. If those ducts get clogged up, then you can get high pressure there in your aqueous humor. Your vitreous humor holds the spherical shape of the eye.
So in other words, if you have the low pressure, you won't have vitreous humor anymore.
If you want now?
If you have your low pressure, you're not gonna have your vitreous humor anymore.
Right, yeah. So like if you had collapse of the eyeball. It holds the spherical shape of the eye. And this isn't drained. You basically have this your entire life. Same. Oh, that's right, not replenished.
So if your eyeball collapsed,
Now you can see the collapsed eyeball. So this is kind of cool. Like the fluid that's inside of your eye, it's the same your entire life. That's why babies are so cute. You ever wonder why babies are so cute? Because they have big eyes. They have big eyes. Their eyes don't grow that much.
oh,
Yeah. My, what big eyes you have, little baby.
So it's really the face that changes in the eye shape.
Yeah, I mean, they change some. They do for some. But they have pretty big eyes, babies. Like, they're sort of freakishly big. Like in the cartoons. Like those princesses in the cartoons that have the really big eyes. It's just sort of this thing that we have, this concept of beauty, that big eyes is beautiful.
So when they do, like, LASIK eye surgery, they're not
Mhm.
worried about, like, piercing the eyeball? I mean, obviously, I'm sure they're worried about that. But what do they, I watched a procedure, and I don't know what to do.
Yeah, I think they actually cut the cornea and they pull it off, and or is it to remove cataracts or something?
I don't remember what it
You're
was.
right.
they selectively have like a sliver of the cornea and like look over, and then they do the procedure.
Yeah, we'll watch a video later. That has to do more with the optics of the eye, but we'll look at that later. We'll watch a LASIK surgery. You want to watch it later?
Yeah.
It's kind of
No, because
gross.
I don't want to know what happens.
Yeah.
The person that I watched, he was able to actually, like, watch it happening.
Yeah, you're awake.
On a video screen above him.
You're awake.
Can you imagine?
I can imagine that'd be good. Like, then you don't have to wear glasses anymore, right? Or contacts. And I know they do many LASIK surgeries,
Do, like,
but when you start messing with your eye, I don't know.
Yeah, but I mean, you should just wait. If you have to have LASIK, you just wait till you're older because I'm too young. Like my eyes are gonna change a lot.
Yeah,
So if I do it now, I might need to have to do it in like 20 years.
yeah.
Okay.
We'll talk about the optics of the eye and all the various issues that you have later. All right. The lens. The lens focuses light onto the retina. Sorry, that's kind of small there. And the retina detects the light. Don't worry about these right now. We're mainly worried about the fluids. But later we'll talk more about the lens and the retina and the cornea too. I'm sorry, what did you say?
So for the test, they just have to do the version.
Right. Yeah, so I want you to know the aqueous humor, the vitreous humor, these issues of high or low pressure, the concept of intraocular pressure, that's the pressure inside of the eye. The other stuff has to do with detecting light, and we'll get that, I think, chapter 7. All right, a tonometer is used to measure the pressure in the eye. If you go to the optometrist, yeah, they like, at a human doctor, it's usually just like a little puff of air that they blow onto your eye. But I'll show you an animal doctor. It's a little bit different. It measures the pressure required to bend the cornea.
They're just like it's like a stick, and they like numb your eyeball, and they just like literally take the stick and just press it down.
No, a tonometer is a little thing they poof, a little poof of air in your eyeball. I have a video. Actually, let's do this, and I'll show you the video. The aqueous humor. This is the fluid between the cornea and the lens. All right, we pointed this out on this graph up here. It's this stuff right here. Is replenished if the drainage is blocked. The pressure becomes too big. All right, that's glaucoma. This can damage the optic nerve. And this is called glaucoma. Oh, that's a G. If there's surgery, or there are medicines that can reduce the amount of fluid that you're producing. But that can be a serious issue, that if you have too much pressure in there.
So how does it damage the light?
I don't know.
Oh.
I'm not sure.
Is there a possible way, I know this is like really painful if it's possible, but is there a possible way that both could happen?
What?
High pressure and low pressure?
Yeah, I suppose you could have low pressure in the vitreous humor and high pressure in the aqueous humor. I'm guessing. I'm not an optometrist or a doctor, so I don't know.
Because they're not connected?
Right, they're not connected because the aqueous humor, it's drained out, but the vitreous humor is not. It remains the same. But again, I'm not really a doctor, so I don't know. Let's watch. I have a video about the tonometer. Let me go ahead and stop this. Sometimes if